Hey guys, welcome to my talk on the sub-Riemannian geometry of MBQC. So what I want to talk about today is the error model in MBQC, and then what can we do with the sub-Riemannian geodesics. So first off, MBQC is a quantum computational scheme that is done via successive measurements on a resource state, and as a convention we have now n times delta qubits where that resource state lives on, and we have an encoded state that lives in a smaller Hilbert space. We want to be in the uncorrelated regime. That means that the successive measurements are far enough apart such that the channel that we implement will be the product of channels that are implemented on all of the sites. Trivial measurements that happen in between those measurements, and they don't affect the encoded state at all. As a quality parameter, we have the string order parameter, and that parameter measures the quality of the resource state. We have a little picture here showing that we have a chain of qubits or some other geometry of qubits, and then measurement in non-trivial basis. Okay, now to the error model in MBQC. First off, we have restrictions to the measurements on each site, and so we have to each site we have a set of generators that can be applied on that site or on that qubit, and it's a subset of Pauli strings on the encoded subspace. Unitary gates that we optimally would implement are just the rotational gates, so e to the I, then some angle that is given by measuring in a respective basis, and a generator that generates the rotation. Channel that will be implemented is a probabilistic mixture of doing that rotation and doing the opposite rotation. And so it's not unitary, but it's slightly altered. Especially if the order parameter is close to 1, then we are very close to the unitary that we want to implement. And as a first thing, we can now look at the error scaling. So we define as the error the difference of the channel that we implement and the unitary that we want to implement. And if we choose the angles accordingly, then we get an estimate of the error that is the sum of errors adding up on each side, and those errors at each side are given by a prefactor and the rotation angle squared. And we also have higher order terms that we neglect. You can see in this plot that this also works numerically for having only x rotations. And now this is our big result, and I will show the steps of the proof afterwards. So we are given a unitary and some resource state. Given that we can only do this set of generators G, we have a sub-Riemannian structure on the Lie group of special unitaries, and with that we define the sub-Riemannian distance of the unitary to the identity, and we can implement this unitary on that resource state with this error bound, and that is our result, our theorem 1, so to say. And most importantly, we have this 1 over n scaling, where n is a measure for the number of qubits in the resource state. And as we see, we can use more qubits to make the computation more exact. Okay, now you're probably wondering, how do we get the sub-Riemannian geometry and the sub-Riemannian geodesics? So that everyone can follow, we have a very simple example. We take the Lie group, SU2, and we only allow gates that are rotations in a direction spanned by x, by Pauli x and by Pauli z. So we have, for example, a sequence or a product of unitaries, rotations in x direction, rotation in z direction, alternating. And we call this restriction that we only rotate in x and z direction the horizontal distribution. So we have a Hamiltonian that only lives, that is just a sum of Pauli x and Pauli z with arbitrary time-dependent coefficients. And now we have a little trick. Look at this in the space of time-dependent Hamiltonians. So we don't necessarily look at the product of the rotations, but at a general time-dependent curve where the Hamiltonian is restricted to our subspace, and we have the boundary conditions that we start at the identity and end at the unitary. And for sub-Riemannian geodesic, we also impose that the length functional, so the time that it takes to go from the identity to the unitary we want, should be minimal. And now we call the sub-Riemannian distance of the identity to that unitary the minimum of all lengths of connecting curves. And analogously, we can also minimize the energy, that is, and this is equal to the minimal length squared. And here we see that we have this error and that it exactly scales with the sub-Riemannian distance. So we have some angle of a rotation in the y direction. That is a rotation that we cannot immediately do with only x and z rotations, but still our estimate holds. And to do that, to go over from this sub-Riemannian geodesic, from this continuous curve, to a sequence of rotations, we use the so-called Lie-Trotter-Suzuki product formula. And this is given by a product of exponentials at half the time. So we slice our geodesics in, let's say, n pieces. And because we only used horizontal curves, we now also know that what comes out are only allowed gates. So if we have a Hamiltonian that has only x and z components, then the exponentials we have here are also just x rotations and z rotations. The individual angles squared, they will sum up to the energy because of numerical integration. That is basically numerical integration, and so we also have an error estimate. Okay, here you now see the Lie-Trotter-Suzuki product formula in action for a sub-Riemannian geodesic that connects the identity and rotation in the y-axis. And you can see it works pretty well. But in general, if we are not in the special SU2 case, it's very hard to find geodesics and to find how long will those geodesics be, or how will the error scale. And therefore we found this ball box theorem, and that connects a norm that can be computed, the so-called maximum norm, to the sub-Riemannian distance. So we get an upper bound and a lower bound on the sub-Riemannian distance based on that unitary. And we can see that these estimates, they work for our case of the x and z rotations available. And yeah, we also have two trivial upper and lower bounds. First the one that is impossible, that we have the angle itself, and the other one would be using the Euler angles of these rotations, so having a pi half x rotation, then a z rotation with the angle alpha, and back a pi over half x rotation. That would be also an upper bound, and this yellow curve is our sub-Riemannian distance. The green and the orange one are these upper and lower bounds we get from this ball box theorem. Okay, how can we go on? How can we improve? So, first our research is related to optimal quantum control and geometric complexity. This term geometric complexity comes from research from Michael Nielsen, circuit model of quantum computing, but it's now extended to the also measurement-based quantum computing. And the optimal quantum control is a bit of a mix going to the experimental side as well, how to implement gates on a real device. But also there we have this notion of sub-Riemannian geometry, or also Riemannian geometry with the penalty metric, trying out this fast marching algorithm, or this is a class of algorithms to compute geodesics, not only for the SU2 case, but for SU4, SU8, and so on. Then what Arnab and I want to do is go to the correlated regime and see if we can find a similar estimate. And what I'm really interested in right now is looking at quotients, because in MBQC we don't implement unitaries necessarily, but our outcomes are these probability distributions, and would be interesting to see how to extend this notion of sub-Riemannian geometry to these quotients that in some cases are orbifolds, and that's also an interesting mathematical topic. Yeah, thank you for listening, and see you next time.